So this is chapter 1 of SER222. We're using Lewis and Chase as our textbook. You can use the 3rd edition or the 4th edition. I don't think that we'll see a big difference. Chapter scope is aspects of software quality and an introduction to data structures. So the aim of this course is software development. Software engineering is really the techniques that support the development of high quality software, and quality is a big part of what we want to do in this course. You're going to get the tools that it takes in order to solve problems and the analytical tools it takes to determine whether or not you've done it well, and or not that you have done it, whether it's going to work well. So be able to predict whether your solution has the potential to work well for problems, especially problems that involve large collections of data. Our focus is on controlling the development process to achieve consistently good results, and this is a really hard problem, and that's what software engineering is all about. There are typically a lot of stakeholders involved in software development. Some important ones are the client, because they're responsible for you getting money, and the user, who actually is going to interact with your software. That may not be the client. Very often somebody is paying you to develop software for other people to use. It's important as engineers that we interact with our clients and model our users well, and make sure that we solve the right problem, which is more difficult than it may seem. People have made their whole career on this. One key that is really important is to interact often and throughout the project, frequently with the client, not just up front to collect stuff. It has to generally happen often. And our goal is a very challenging one, not often met, to deliver a solution on time and under budget. But in order to do that, there are trade-offs that have to be considered, and you need to be able to estimate and predict stuff well. We want to be able to deliver a high-quality solution, but quality, what you think as a developer is quality, is almost never going to be what the stakeholder cares about. In fact, often the easiest things matter the most to them, and the stuff that you want to do that matters the most might just be perceived as wasting time. We want to accomplish this all in an ethical manner, which really means that you want to make sure, well, you want to be professional. You want to let the stakeholders know as soon as a risk is identified. You need to let them know, not after they've already paid the price. And you also want to make sure that credit is given where credit is due. If you find yourself using open source software or other thing, make sure you understand the licensing and so forth. So this slide, I think we can spend a fair amount of time on. It's aspects of software quality. It's just one slide, but I'm going to talk through it quite a bit. So probably the most obvious is correctness. Now, believe it or not, you can sometimes get by with things where they're not correct. But mostly, correctness is something that somebody just assumes first, and then given that it's correct, now let's optimize something else. So there are techniques that can be used to prove correctness. People have invented entire systems, entire programming languages aimed at proving that other software is correct. But in general, software systems are so large and complex, and in general, they're not understood well enough that you can say that the whole system is correct. And usually, people just shift them, knowing that they're not completely correct, but that they'll fix the problems that are important as they're encountered, if they're encountered. So that gets into reliability. So software is going to fail. So how often does it fail, and how critical are those failures? So one hopes that you don't often have critical failures, and the more critical, the rarer you would hope it is, if ever. And then when it does fail, so if you just accept the fact that software might fail, you've got the well, what do you do when it does fail? Does random, unexpected things happen? Does a user lose their data? Do they just have to restart the program? Or does a satellite crash into Mars? So it's kind of, what do you do? I mean, sometimes you can recover when something goes wrong. You can catch it, and you can resort to a fallback, or at least patch the thing in some way. And then there's usability. Difficult to measure without user studies, and This is something where, if you make it usable, that can be really good for marketing, but maybe not. You can't sell anything if you don't have it first, so usually the priority is to get it out on time. Maintainability. So in engineering system, maintainability becomes important, because if we recognize that it's never correct, it's hopefully reliable, then what's going to happen is we're going to need to go back and fix and fix and fix. And other people other than you are going to have to be, a new engineer is going to have to come in and work on it. They need to be able to do that. So how easy or difficult has your solution made that? One way to keep things maintainable is to not do anything unexpected, and to keep what you're doing simple and clear, and adhering to known programming and software development constructs, known patterns that other people would recognize. And that kind of leads into reusability. So the ease with which components can be reused in the development of other software systems. So if you can reuse them, then you need fewer separate components, maybe more design, but less development, less testing is needed for each little unit, because you're reusing the same one multiple times, and less cognitive overload, right? So, and then portability. So how well can they be moved to different environments? Sometimes that's not a concern at all. Sometimes you don't think it's a concern, and then all of a sudden it is. And then efficiency. So, and that's really going to be the bread and butter of this course, where one assumes, a lot of these are difficult to quantify, and it's just going to take experience and judgment and weighing. But efficiency is something where we have some analytical tools to support it. So it gets tricky how you measure efficiency, and one of the reasons it gets tricky in computer science is the performance of a system just naturally increases over time. There's Moore's law. It just gets better, and for a while it just has constantly been getting better. That's tapered off a little bit, I think. But so how efficiency do you do it? How much resources do you waste to solve it? So resources are typically memory or time usually, right? And that's kind of going to be a big thing that we think about when we talk about algorithms in this class. So what is a data structure? That's the name of the course. The data structures in this book lay the foundation for developing complex software. What does this mean? In this book, we're not going to deal with, because in 200 you've already dealt with objects and classes and interfaces and abstract classes and polymorphism, and you kind of know how to group data in Java. You know how to encapsulate things with methods. You've learned all of this stuff in 200, and you still remember it, right? So, and you know what a constructor is and all of those things. So, you hopefully you understand that. So we're not talking about a data structure to describe a person. This course is, for instance, or an animal or a widget, right? This course is about data structures to manage large collections of things, and in particular, collections of things which can grow arbitrarily large. So 100, how does it work for 1,000 items? How does it work for 1,000,000 items? So a data structure that can manage a large database, the inventory of Amazon or something like that. It could be something simple, like the pixels in an image, or in a mapping application. How can you design a data structure that can represent the streets and that are connected to different sites, different points like addresses, and design that data structure so that because of the way your data is organized, you can answer questions efficiently. Like, what's the shortest path from route A to route B? So there's going to need to be some sort algorithm, and hopefully if your data structure makes it easy to come up with the shortest path, or maybe you need multiple paths between the same points. And depending on how you organize and design the data structures to represent streets and speed limits and intersections and sites and points on a map, that could be much easier or much harder. And so there's these fundamental, very abstract theoretical data structures that don't depend on how it's implemented, and then all kinds of engineering details that go into it as well. So as we discuss data structures, we're going to practice good software engineering, and in particular we're going to apply these things in Java in this class. So you're going to see it in Java. So data structures, it's good to think sometimes of a tangible, physical thing that you could pick up and hold, analogy to a data structure. So physical, an example of objects to manage could be shipping containers at a dock. And so they got to be managed carefully and efficiently, right? None can be lost. So fortunately, in computer programs, physics don't usually matter, but sometimes they do. But you don't want to stack them up so high they're going to fall off the boat. And there's other things so you don't want to arrange them so that they become the one that you need to get is inaccessible because it's buried under ones that you don't need to get. You don't want to waste time searching for the container that you need to unload at a particular site. So there might be some that need to come off first and some that need to come off later, and where do you put them on the boat? So there's a lot to think about, and it's good to sit there and model the problem quite a bit. Recognize that containers are generic. They're all the same shape, they're all the same size, but they contain different cargo. That you need to know which container is which, so they have some sort of identification number, so you know which one to grab to load and unload. You got handlers, but the handlers don't necessarily need to know what's inside the container. But maybe they do need to know that if it's handled with care, or it shouldn't be flipped upside down, kind of thing. Maybe there's what information do you need to know about the containers? A lot of issues come up. So how many containers might you need at any point? Sorry, I'm trying to move myself out of the way. There you go. How many might you need at any point? There's a wonderful image from the web. We probably don't want this solution. Maybe this solution just feels a little bit nicer. How are you going to arrange them in one big line, sorted by ID so that you can find the one that you're looking for quickly, in ascending order and descending order? Does the order in which they are going to be loaded or unloaded matter? Yeah, so that gets into, so if you were to stack them all up, then the order that they're unloaded has to be the opposite of the order that they're loaded, right? So you need to think about that. But it turns out there's no one solution that addresses all the issues adequately. Like I said, sometimes if you stack them, it reverses the order that you unload them. Sometimes you want to just take them in the order that you arrive because you need to get them on the ship quickly, and maybe you'll have more time to unload them, or somebody else is paying for it. And sometimes, more complex, there's so many things going on that a really complex solution might be required. Just to let you know that this problem isn't just completely a toy issue, here is a video from online. The 3D bin packing problem is somewhat similar to what we're solving here with the packages on a boat. It turns out to be, in the theory of algorithms, one of the more complex ones. It's in the class called NP, which means that people haven't really ever found a very good solution for it, and they don't know if there is a better one. So you could keep looking, although people are skeptical that you'll find a really great one ever. So this is somebody's approximate best way to pack a box. If you can find a better way to pack boxes into a larger box without wasting the least amount of space, then I think you'll get $1 million. I'm not sure. So it's not a toy problem. It's a very significant real problem that would have big implications. So with that, I'll end this presentation. Thank you.